contents, and getting started. Congratulations, and thank you for purchasing your CX system from Mala. You have purchased the most user-friendly radar-based concrete imaging system available from the world leader in innovative ground-penetrating radar solutions. Before you get started, there are a few things you need to know to be successful in the field and enjoy many years of successful operation. Upon arrival, please be sure to inspect the shipping case for any damage that may have occurred during shipping. Your CX case is rugged and can withstand years of service, but there is always a possibility of mishandling and damage from the freight company. In your CX shipping case, you should find the following important documentation and items: CX12 monitor, high-frequency shielded antenna, mini cart, USB pen drive, includes Mala 3D vision and supporting software, CX manual and warranty registration procedure, battery, battery bag, battery charger, battery power cable, and AC power source. Please go to the Mala website at www.malags.com and go to Service and Support and fill in the requested information. A username and password will be emailed to you. Then go to Product Registration and fill in required information. The serial number is found on the back of the CX monitor and on the side of the high-frequency antenna. The FCC registration is required for all system sales in the U.S. only. Please fill out the document and send it to the FCC address on the form. Charging your CX batteries. Your CX may be operated with either the battery pack supplied or from AC power via a wall receptacle. Prior to operating with battery power, charging is necessary. To properly charge the batteries, it's important to first plug the batteries into the charger and then plug the charger into the AC outlet. A green light on the charger indicates the batteries are charged. It is very important that prior to using the charger again, the charger must be unplugged from the AC outlet until the charge status light is extinguished. This is necessary to reset the charger. Assembly. The CX requires minimal assembly to get started. The main components for your system are the CX monitor, an antenna that is either 1.2 GHz, 1.6 GHz, or 2.3 GHz, a handle assembly, standard AC power supply, 12-volt lithium-ion battery, mini cart for the antenna, and grid templates for 3D imaging. The CX12 is designed for minimal setup time in the field for maximum productivity. Prior to turning on the system, connect the antenna to the CX unit. Ensure that the antenna connection is secure, which is indicated by feeling and hearing the connector click into place once twisted clockwise. Secure the cable in the strain relief assembly. To connect the power supply, insert the power cable connectors to the receptacles on the CX unit and the battery respectively. Proper alignment of the connector is facilitated by lining up the red dots on the connector and the receptacle. If you are using the AC power supply, insert the plug into the nearest outlet or extension cord. Insert the power cable connector to the CX unit receptacle in the same manner as the battery cable. There are two connection ports at the rear of the antenna. When looking at the back of the antenna, the port to the left is for the distance encoder cable, and the port to the right is for the handle control cable for remote menu operation. To use the mini cart, first attach the encoder cable affixed to the cart to the left connection port. Next, attach the handle control cable to the right connection port. Then place the antenna under the cart. Be sure to line up the bolts on the cart and the studs on the antenna. Turn the bolts so they insert into the studs on the antenna, but be careful not to over-tighten. The single wheel encoder can be attached in two locations, either in the back or along the side. This enables users to change the polarity by 90 degrees if they desire. Sometimes horizontal reflections or weak targets become more prominent when the polarization is rotated 90 degrees from the normal direction. Next, attach the encoder cable affixed to the wheel to the antenna. The optional handle system supplied with your CX unit allows the operator to collect data while standing or to reach ceilings and walls. Plug the handle assembly cable into the back of the antenna. Line up the forks and the studs, and then adjust the telescoping handle to suit the operator's height. Powering up and booting. To power up the unit, press the power button on the CX monitor. The red LED light will illuminate and begin to blink. The monitor will perform a boot sequence, and you may notice several text messages on the screen. This will last about 30 seconds. Your CX system has a user-friendly interactive screen. Commands are entered with the black knob by simply rotating the knob and highlighting the icons on the screen. To activate the submenus, simply push the knob. Your CX can also be controlled with the buttons on your antenna. The red button moves the cursor down, and the black button moves the cursor up. To make a selection, depress both buttons simultaneously. Screen overview. The screen is designed for ease of use in the field and displays certain project types at startup. The three project types are 2D project, 3D grid project, and object mapper project. Each project type has a slightly different scheme, so a review of each project type individually is necessary. 2D project general settings. The first and most common project mode used in the field is 2D project. The 2D project should be your first choice when arriving at your worksite. Scans in 2D project mode quickly give an idea of the concrete conditions and an initial indication of the layout of the structures in the slab. In most cutting and coring situations, 2D project scans yield sufficient information to give an accurate representation of the structures. However, there may be occasions that the 2D project information is confusing or difficult to interpret. Two very powerful tools available to the operator to aid in interpretation of the data are migration in the 2D view and the 3D grid project. Use of these tools will be discussed later in this video. Once selected, the 2D project leads to a general settings screen. This screen is very similar in all data collection modes, and the functionality is the same in all modes for these icons. However, there are some slight differences in each mode, which will be discussed later where applicable. In the general settings screen, you can select the antenna. Normally, the CX12 auto-recognizes the attached transducer at boot up. Select the depth window. Find the zero depth. Adjust the filters if they've been activated. Select the acquisition mode. Adjust the appropriate point interval time interval. Select the type of measuring wheel. And select the material type. The general settings screen also displays the trace and radar gram for the attached antenna. You can check to ensure the antenna is connected correctly and that the zero depth is calibrated using this display. Select antenna. To select the appropriate antenna, move the cursor over Antenna and click the knob or simultaneously press the antenna buttons. A drop-down menu is displayed allowing the selection of the 2.3, 1.6, and 1.2 GHz antennas. Select the appropriate antenna. If you have a built-in EM sensor on the 1.2 or 1.6 GHz antenna, the CX12 will connect to it automatically. Select Depth Window. The depth window is essentially the range to which the radar signal will display data. The setting is dependent upon the thickness of the concrete to be imaged or the depth of the interest in the slab, wall, or ceiling unit. By selecting the depth window and clicking on it repeatedly, you can cycle through your 3 depth windows: shallow, medium, and deep. The amount of data displayed in each depth window will depend on the antenna selected and the current material type. For example, if using a 2.3 GHz antenna in reasonably aged or cured concrete, the approximate time window will be shallow, 7.8 inches, medium, 14.1 inches, deep, 20.4 inches. Please note, because the depth window is set to deep, which in this example results in 20.4 inches of data on screen, it does not mean radar waves are actually producing useful data to that depth. It is up to the operator of the system to interpret how deep the antenna is producing useful data. As the antenna loses depth penetration, the data becomes noisy and less interpretable. Find zero depth. The zero depth search is accomplished with the push of a button on your Mala CX12. To begin, place the antenna on the surface to be scanned and then select Find Zero Depth. Then push and hold the knob or the antenna buttons until an audible beep is heard. Please note, by default, your system is shipped from the factory with the exact filter settings required for the majority of circumstances encountered in the field. These default settings are dependent on antenna selection. In the event the user requires adjustment of the filter parameters, it is possible to activate the filter setting menu by contacting your authorized Mala representative. Select Acquisition Mode. Wheel mode. This is the most common method of acquisition, which includes the mini cart and the single wheel operation. Time triggering. Select time triggering to run continuous scans without a wheel device. This is useful for areas where it's difficult to maintain contact of the wheel and the surface. Please be aware that in this mode, no horizontal distance or location of information is recorded with time triggering. Adjusting the point interval, time interval. Point interval and time interval settings allow the user to change the number of scans from the antenna per unit distance or time if in time mode. A typical setting for a concrete investigation is to trigger the antenna every 0.2 inches of lateral movement across the surface. The higher your trigger interval, the sharper the hyperbolas appear because less data is collected over a given distance, essentially compressing the data on the screen. Select your measuring wheel. There are 2 wheel options on the CX12. The HF black wheel, selected when using the single measuring wheel, or the RTC mini cart. Select the material type. By selecting Material Type on the General Settings menu, the Material Type menu appears. There are 10 total material types to choose from, each of them with their own velocity range. Most important for concrete investigations will be the concrete or user-defined setting. If you are unsure where the material velocity will fall, the preferred method is to use the Velocity Wizard. By selecting the Velocity Wizard, the screen switches to a modified data collection screen. Please note, selecting the proper material type is integral to obtaining a reasonably correct velocity. A correct material velocity provides the most accurate depth scale for depth measurements to a target. The depth reading and image on screen is based on the principle that the GPR signal is traveling through the concrete at a given velocity. Variations in the concrete material may cause the signal to travel slower or faster than your chosen velocity, which may result in inaccurate depth readings. The Velocity Wizard. In order to properly calculate the velocity, it is necessary to have some data to work with, preferably collected over the area you wish to scan. To collect 2D data for the Velocity Wizard, select Start. After selecting Start, the data portion of the screen turns black, followed by an audible beep. Push the antenna and data appears on the screen scrolling from left to right. Adjustments such as gain and screen contrast may be changed if necessary at any time during data collection as needed. A primary objective for the initial scan is to locate targets that exhibit well-defined hyperbolas. Once a representative hyperbola is identified, press the stop button, which is followed by a second audible beep. Notice the migration and hyperbola icons are visible and available to the operator. Both migration and hyperbola matching are industry standards for velocity calculations. Migration automatically collapses the hyperbola to form a single line or point of an object, removing unwanted artifacts and sharpening the image. Hyperbola matching. Hyperbola matching utilizes a graphical hyperbola the operator fits to that represented in the data, in turn automatically adjusting or calibrating the CX velocity to the concrete scanned. To implement the hyperbola matching function, 1. Move the antenna backwards and line up the cursor at the midpoint of a representative hyperbola in the scan. 2. Select Hyperbola On. 3. Use the X and Y position command buttons to move the graphical hyperbola over the actual hyperbola in the scan. Four. Once the graphical hyperbola is centered on the actual hyperbola, select the velocity icon to match the shape of the hyperbola. Matching the graphical hyperbola to the actual hyperbola gives an approximate velocity of the concrete or other media and automatically calibrates the depth scale. Migration. To use migration, select the Migration button. A processing box appears on screen, followed by the migrated data produced from the selected velocity. You may need to adjust the contrast filter to enhance the image on screen. Using the Velocity button, adjust the velocity up and down to collapse the hyperbola to as close to a singular point object as possible. Once a point is displayed in the place of the hyperbola, the corresponding velocity for the concrete being scanned is approximated, and the depth scale is automatically calibrated. Once you have completed one or both of the velocity routines, a reasonably accurate velocity of the material scanned is established, and hence more accurate depth measurements to embedded targets are realized. Select the Exit button, and you will notice the user-defined material type now displays your correct velocity. Select OK to store the information and return to the General Settings screen. Select Continue at the bottom of the General Settings screen to begin data collections. The initial setup of the CX12 is now complete. This process is similar in each of the project modes, whether 2D or 3D. Data collection in 2D mode. To collect 2D scan data, select Start. Move the antenna along the slab, wall, or ceiling. Typically, you may need to perform a few scans to ensure the settings are optimized for the site. The first thing you will notice is the screen turns black. Push the antenna and you see data appear on the screen scrolling from left to right. Adjustments such as gain and screen contrast, and perhaps point interval may be changed if necessary. We will discuss when and how to change these settings in this section. While collecting data, there are 6 icons you may select. Stop, which ends your current profile. Screenshot. This command captures a full screen of data and stores it on your CX as a JPEG file. To take a screenshot, simply select the screenshot icon and activate it using the knob on screen or by depressing both antenna buttons. The screenshot will be stored in your CX12's memory as a JPEG file. A JPEG file is easy to email and can be integrated into presentations and reports without any special proprietary software. The next icon is the background removal filter. Highlight the icon and press and turn the knob to increase the amount of filter applied. The filter is designed to remove unwanted horizontal bands of noise which are endemic to most radar data. One word of caution regarding this filter is that any data that is horizontal in nature, such as the bottom of a concrete slab and/or tracking parallel to a post-tension cable, may be removed from the radar data. The following is an example of data without the background removal filter turned on. This is with the background removal turned up to high. Typically, you will use this filter turned on very slightly, as shown in this example. The next button is the screen contrast. This function is very sensitive, and very small adjustments make a large difference in the contrast of the data. The triangle in the icon indicates the level of contrast you have selected. Contrast can be adjusted to bring out weaker targets as well as tone down strong reflectors. One should not overuse the contrast, since over-contrasting can make the data unreadable. The following is an example of data with too much contrast applied. This is not enough contrast, and this is just about right. The next button is the exponential gain. The exponential gain function is similar to the contrast. However, the gain amplifies targets to a greater level the deeper they are. This prevents overgaining the data in the near surface, where less gain is needed to enhance targets versus those at depth. This will work well for helping to image the bottom layer of rebar, as well as the bottom of the slab. As with the contrast, you can overgain the data with the same detrimental effect, so optimally, you should try to balance the images. The following is an example of too much, too little, and this is just about right. Markers. Using 2D scan mode, you may use a marker to inscribe in the data. For example, if you scan over a surfaced feature such as a floor drain, outlet, or any other surface item, you can electronically mark its location by selecting the marker button. Once data has been collected on the screen, if you select Stop, you will notice the data will remain there for interpretation. All of the filter buttons will remain available to you, as well as the screenshot and marker buttons. The migration button will now also be available to the operator once Stop is selected. This will give you the opportunity to migrate the hyperbolas you have on screen, giving you clearer images for more congested areas. This will also help in imaging the bottom of the slab, as the tails from the hyperbolas sometimes cover the reflector from the slab bottom. While the data is migrated, you can also take screenshots to integrate into reports. After selecting Stop, select Migration. A processing message window appears and the data is migrated with the listed velocity from the last project. Properly migrated data collapses the hyperbola to a point object as discussed previously for the velocity wizard. If the previously assigned velocity does not optimize migration to a point, adjust the velocity up or down accordingly. Select Exit or select New Profile. The EM option. Mala Geoscience was the first GPR manufacturer to incorporate an EM sensor into a GPR antenna. The EM sensor allows the user to detect EM fields that emanate from energized electrical conduits or cables. The EM sensor is a passive sensor that detects 50-60 Hz EM fields only from embedded cables that are live. As the GPR antenna with the EM sensors is moved across the EM field from energized cables, the field is represented along the bottom of your 2D data screen. One line is red, which represents sensors on the right side of the antenna, and one line is green, representing the sensors on the left side of the antenna. These two lines will rise and fall depending on the direction and strength of the EM field as the antenna moves across the field source. Essentially, any disturbance or perturbations in the red and green lines from horizontal are indicative of EM energy emanating from the slab. EM fields often bleed over onto other metal structures in the concrete, skewing the image quality of the EM data on screen as either broad anomalies or simply noisy or rapidly changing indications of the red and green lines from horizontal. Detecting and tracing targets. The most important function of the 2D project is to quickly allow you to trace out and mark targets of interest in the concrete slab. To locate targets of interest, simply move the antenna backwards along the same path of the displayed profile. The cursor that appears on the screen may be centered at the midpoint of the hyperbola. The operator can then mark the location of the target of interest on the concrete surface by aligning the chalk or other marking material with the hash marks inscribed on the antenna. Please note that hyperbolas vary in dimension based on how the antenna is aligned with an embedded target. A hyperbola is of minimum size when the antenna is aligned exactly perpendicular to an object such as rebar or post-tension cable. To trace an object such as rebar or other embedded targets of the concrete, the operator can simply repeat profiles along parallel paths and continue to mark the target in the area of interest. Please note that to effectively scan an area in 2D, the operator must perform the scans in at least two perpendicular directions. In complex slabs, it is generally advisable to perform both 2D and 3D surveys. Grid projects. Grid projects are an excellent tool to aid in interpretation of a congested slab. Collecting multiple scans along the provided grid templates allows the creation of 3D images of the structures within the slab. Grid Project Mode allows the CX user to image these structures and scroll down through the different depth slices as if each layer of the slab is peeled back to expose a given surface. This is especially helpful in situations with conduits or other embedded objects cutting across the grid at various angles, as well as post-tension cables that typically ascend and descend through a concrete slab. To begin 3D imaging, select Grid Project from the main CX Project screen. The Grid Project General Settings menu appears with the same information you entered for the 2D scan. Settings can be changed here if needed. Two settings that are absent are the acquisition mode and the point interval, as the grid projects can only be completed using a wheel for data acquisition. Once the correct settings are entered and the correct zero depth has been found, you can select Continue. The Grid Project Manager appears with default values for the standard grid mat, either 32 inches by 32 inches or 80 centimeters by 80 centimeters. If you do not wish to use the standard grid paper, you can make the grid as large as 55 inches in any direction or as small as 8 inches. The default grid size is recommended. By selecting the Use Standard Carpet icon, the grid size reverts to the default grid paper at any time. In this example, we will use the standard grid carpet. Select Continue. The next menu is the 3D Grid Project Overview. This is a good time to review the settings before starting the project. If the parameters are satisfactory, select Start. Basic information about the grid project appears next to the graphical screen representation. The red triangle on the screen graphic is indicative of the antenna position. Place the antenna at the Start Here First direction parallel to the y-axis, which is also line 0 on the grid template. Line up the permanent hash marks inscribed on the antenna with mat origin. Press the black button and scan to the end of the grid by aligning the inscribed hash marks on the antenna with the grid endpoint. The data line will stop automatically, and at this time an audible beep is heard. Depress the red button to proceed to the next line, and another confirmatory audible beep is heard, and the red triangle appears at the beginning of the next profile ready to scan. Repeat the process until the system graphical interface indicates that the grid profiles for the X direction now need to be scanned. Perform the scans in the X direction exactly as for the Y direction. Please note that you must move the antenna to the endpoint or proceeding to the next line is not allowed. If the profile is of insufficient length, the system will prompt the user with a dialog box indicating the profile is not complete. When the grid project is complete, select Process. After about 1 to 2 minutes, depending on the grid parameters, the system will automatically process the data to create a 3D image. 3D grid processing. The system will default to a split screen depicting both the cross-section 2D view on the right side and depicting the 3D image on the left side. The CX system's 3D imaging capability relies on the principle of migration described heretofore in the 2D function overview for depth calibration. An important step to achieve an optimized image of the concrete media is to scroll through your data selecting the X or Y icon. The 2D window on the right side of the screen is the non-migrated view of the profile. Scroll through the profiles until you find a good representative hyperbola. This profile is what you will be using to adjust your velocity settings for optimal migration, so be sure you have several hyperbolas on screen that are a good representation of the grid project as a whole. To optimize this process, select the wrench icon and select Velocity Settings. From this menu, you can adjust the gain while completing the migration, and you can adjust the background removal filter. In the Velocity Settings, the selected 2D view is displayed from the Velocity Settings menu. Turn the migration to On and adjust the velocity level to change the shape of the hyperbola. As you increase the velocity level, you will notice the hyperbola begins to collapse. Continue to increase the velocity until you have a singular point instead of a hyperbola. The following are 3 examples of migrated data. Example 1, under-migrated. Example 2, over-migrated. Example 3, just right. Please note that the same filters are available in the velocity settings as is in the other CX menus. Once the data is properly migrated, select the OK button to apply the changes to the main grid project. The system then reverts back to the grid project processing screen. From the grid project screen, one can scroll up and down through the 3D concrete volume by selecting the depth icon and moving the horizontal cursor on the 2D window up or down. The depth of the image surface is displayed within the icons or along the vertical axis of the 2D section. 3D grid processing. There are several processing features available in the grid project mode that are not available in other data collection modes. The 3 larger icons displayed underneath the 2D screen are Angle, Aperture, and Threshold. These 3 icons can aid in the interpretation of the 3D image data and are typically used at the discretion of the operator depending on the data set and the complexity of the media. It is safe to say that the operator must determine if any of these features have the intended effect to aid in interpretation on a case-by-case basis as well as experience. Angle. This feature corrects the 3D image for grids accidentally performed off-angle or not parallel or perpendicular to the actual rebar mat. For example, if the grid mat lies 30 degrees to the actual rebar alignment, the 3D image will be distorted. Rather than move the mat and begin the data collection process over again, the operator can simply enter the angle and the CX automatically corrects the image distortion. Aperture. The aperture feature allows control of the thickness of the data slice depicted on the planned view. As the aperture value increases, the horizontal cursor becomes wider. Widening the cursor displays more features at a given depth slice, aiding in interpretation. However, If one wishes to estimate depths to a target off the plan view, the error is dictated by the amount the aperture is open. Threshold is useful for suppressing unwanted low-amplitude background noise from the data. Increasing the value may sharpen the desirable target, such as rebar, while suppressing weaker reflections and, in ideal circumstances, will render only the rebar in the image. EM Plan View. For grid projects collected with an EM sensor-equipped antenna, the user can also activate and view the EM sensor data in a 3D plan view. This allows correlation of the GPR data with the EM sensor data. EM sensor data viewed in plan view can aid in interpreting the trend of the EM signal and hence give an indication of the trend of the conductor of the slab. To activate the EM data, simply select the EM button from the grid project screen. It may be necessary to increase the gain to bring out the EM signal data. Once all of the settings are optimized, select the full screen icon. Drill Locator. A very useful tool for cutting and coring applications is the Drill Locator tool. In this menu, select the full screen option. Now use the X and Y icons to place a crosshair over an object or areas that are clear of any objects. Select the circle icon to place a virtual core hole over a location that may be desirable to core. Adjust the size of the drill locator to the size of the intended core to give an indication of what the actual core might intercept. Please note that the drill locator is an approximation and is intended as a guide only, and that extreme caution while actually drilling is warranted. JPEG Screenshot Feature. Another feature in this menu is the Camera feature. Select the camera icon and snap a JPEG image of the 3D slice with the drill locator or any other portion of the image. The image can then be uploaded to the USB memory stick supplied with your CX for presentations or archival purposes. 3D Slice Movie. Using multiple screen images, a time slice movie of the 3D data set can be created. To create a 3D slice movie, select the wrench icon from the Grid Project processing screen. From the drop-down menu, select Time Slices Gen to access the Time Slices image generator screen. Now, select how much data is desired to image using the depth range setting. The entire data set or only sections can be selected. Input the number of depth slices to split the depth range into. Select the desired aperture to apply to each slice. Select Generate, and the CX will automatically generate the images as a movie from the Grid Project. The images will be stored under the file name listed under Last Saved Folder, and will be accessible through the Work with Files icon on the main project screen. Object Mapper Projects. The final project type available is the Object Mapper. An Object Mapper project is a tool to easily handle and interpret a large number of radar profiles collected parallel starting from a common baseline over a larger one. The typical Object Mapper project is completed when you need to trace and map certain structures over larger distances than can be handled in the Grid Project. It allows you to organize your data so it can be easily imported into the Object Mapper software. Select the Object Mapper icon and you'll be brought into the General Settings screen once again. As you will notice, it is the same settings available as the previous two projects. Look over your settings to make sure they're correct. Find your zero depth and select the Continue button. Once in the Object Mapper settings, you'll be able to adjust your baseline direction and your line spacing. Your baseline direction will depend on which direction you plan on expanding out with your data collection lines. Line spacing will be the distance between each consecutive grid line. Select Continue, and you will come to the data collection screen. Select Start to begin data collection. Push the antenna the desired distance and select Stop. Move the antenna to the next desired data line and select Start again. You will notice the baseline information in the bottom left of the screen has increased by the amount given for your line spacing. Continue collecting data until you've completed your area of investigation. After the last line is collected, select the Exit button, which has appeared at the bottom right of your screen. This will bring you back to your main project selection screen. The data can then be downloaded off of the CX12 and uploaded onto a computer with the Object Mapper processing software for further interpretation. Working with files. The CX12 will store all data from the different projects collected with the system. To transfer or delete them, you will use the Work with Files button from the project screen. This will take you to the File Interface menu. In this menu, we can select and mark different files using the Selector knob on the monitor. Once files are selected, they can either be opened, deleted, or uploaded depending on your goals.